We don't have a ton in common with cavemen. Draping ourselves in animal skins, carrying around big clubs, all went out of style a while ago. But there's one thing that both cavemen and modern educated people both appreciate and fear a healthy amount. Today, we're talking about everyone's favorite marshmallow heating method, fire. We'll be learning how it burns with different fuel, why it looks the way it does, and why it's actually not an element like the ancient Greeks previously thought. I'll also have some wild examples of animals and plants that have come to depend on fire as part of their survival. From the first strike of the match to safely extinguishing the flame, by the end of this video, I guarantee you'll be stoked. Hey, I'm Miranda Cosgrove, and welcome to my STEM loft, where I'm really worried I'm gonna drop my phone down the gap between the elevator and the floor. Is that normal? Fire first gave humans the ability to cook food. It provides a portable source of heat and light. It allows us to forge metal tools and fire pottery, and even drive power plants. It also makes the baton twirling routine way more exciting. But for all the ways fire benefits humans, it causes an equal amount of harm. A fire can rage out of control in less than 30 seconds, burning down your house and all of your belongings. It gives off a dangerous amount of heat and smoke. Fire is more deadly to humans than any other force of nature. Understanding its characteristics and how to treat fire safely will not only reduce its potential harm, but empower everyone to use this incredible tool. So what is fire exactly? There might be something to that old Greek myth about Prometheus stealing fire from the gods, because its qualities are pretty out of this world. The funny thing is, fire isn't exactly made up of matter like the other classical elements, earth, water, and air. Fire isn't really a physical thing at all. It's energy. What we're seeing is infinite chemical reactions going off simultaneously in a process called combustion. It's basically a speed run of chemistry. But wait, we can see it and feel it. Isn't everything physical made of matter? I like the way you think. Being skeptical is the mark of a good scientist. That and the insatiable desire to one-up Bill Nye. Fire is more like a verb than a noun. It's an action. It's the process of matter changing form, an exothermic chemical reaction giving off light and heat. Combustion, aka burning something, creates a physical and chemical change in matter. Fire catalyzes oxidation, the process of something combining with oxygen, like rust, but much faster and more dramatic. So how is fire created? 3 components are needed, often referred to as the fire triangle. Typically, fires start when some type of fuel comes into contact with oxygen in the atmosphere, setting off the chemical reaction. Fuel could be something like wood or gasoline. Fuel stores potential energy, which can be released as heat when it's burned. But fuel doesn't spontaneously catch on fire all the time. We need one more ingredient in our recipe for fire: the ignition temperature. And each type of fuel has a different ignition temperature. With the fire triangle of heat, fuel, and oxygen complete, we have everything we need to start our fire. Let's look at a classic, a wood-burning fire. Combustion of wood occurs through 2 chemical reactions. The heated wood releases gases, and then those gases react with oxygen in the atmosphere. First, the wood needs to get hot, like really hot. This could happen lots of ways, from a match, friction, a strike of lightning, focused light, or maybe from something that's already burning. When the wood gets hot enough for its cellulose to start breaking down, about 300 degrees Fahrenheit and 150 degrees Celsius, its decomposing material becomes volatile and released into the air as different gases. We call this smoke. And you know the old saying, where there's smoke, there's fire? So let's turn up the heat a bit. Now, the burn can begin. When the volatile gases heat up to about 500 degrees Fahrenheit or 260 degrees Celsius, the compound molecules break apart, binding with oxygen to create byproducts like water and carbon dioxide. The wood left behind becomes char, which is almost entirely made of carbon, and also ash, which is made up of the wood's unburnable minerals like calcium and potassium. The ignition temperature only needs to be available at the start. In theory, a fire can keep burning indefinitely, so long as there's enough fuel and oxygen to keep it going. Let's investigate another type of fuel to look at complete and incomplete combustion: Methane, or natural gas, is a fuel we use on gas-powered stoves to cook our food. When methane undergoes complete combustion, that means enough oxygen is present to burn the fuel completely, and the byproducts are water vapor and carbon dioxide. Under a limited supply of air or oxygen, burning methane undergoes incomplete combustion and can release carbon monoxide and water, or carbon and water. What are some of the effects of these byproducts? Water vapor is fairly harmless, though not to my steamed broccoli. Carbon dioxide is a greenhouse gas that contributes to global warming, but we also just release carbon dioxide every time we exhale. Carbon monoxide is a little scarier. It's toxic, but it's also colorless, odorless, and tasteless, which is why servicing your gas appliances and checking carbon monoxide detectors are so important. Without these, it's very hard to know if you're getting carbon monoxide poisoning. Unburnt carbon is a type of particulate or pollutant in the air, so also not the best. So now we know the basics of combustion and how a fire burns with common fuels. Now, let's learn about why it looks the way it does. The color and shape of a fire's flame depends on heat, fuel, oxygen supply, and gravity. Its color primarily comes from how hot the flame's burning and the fuel being burned. As carbon atoms heat up, they begin to rise and emit light. This is called incandescence, the same science that makes a light bulb work, and it's why we can see fire at all. The different color variations within a single flame is caused by uneven temperature. Usually, the hottest part of the flame, the base, glows blue or sometimes white, while the rising, cooler parts glow orange, yellow, or even red. On the stove, the methane flames appear blue because an even more efficient and complete combustion is occurring. There are other variations in color too, like burning magnesium produces a bright white flame because its ignition temperature is so hot, 3,100 degrees Celsius. The shape of the flame, on the other hand, is largely created by a process called buoyant convection. As air is heated above the fire, the air particles move further away from each other, making the air less dense. On the other hand, particles at the top and sides are further away from the heat source and become colder. Therefore, the hot gases from the flame rise up and gravity pulls cooler, denser air to the bottom of a flame. Check it out. You can see the flame is forced to escape upwards towards the area of less pressure. Together, this creates the typical flame point near the top and flickering effect. I asked for a flamethrower for this demonstration, but apparently that's incredibly dangerous. So on Earth, a flame ends in a point because of gravity. But what about in space? In microgravity, flames are spherical. The gravity-driven flow created by convection can occur, and flames aren't as buoyant, so they stay put. That means your space birthday cake would look like a lot of little orbs on your candles instead of a typical flame. Okay, back to Earth. Fire can also do a lot of good for the environment on our planet. Low-intensity fires and prescribed burns can clear built-up plant material in ecosystems and recycle nutrients back into the soil to make it more fertile. These controlled burns also reduce the risk for damage and carbon pollution caused by larger, out-of-control wildfires. Some species also need fire to reproduce and thrive. Lodgepole pine cones are sealed with a resin that requires being melted by heat to release its seeds. And some types of lilies germinate or bloom best in the wake of fires. Then there's these little guys called fire chaser beetles. They have special organs that help them detect fire with infrared radiation so they can lay their eggs in recently burned areas. Wild lupine, a plant that thrives in post-fire environments, is an essential food for the endangered Karner blue butterfly caterpillar. These more robust plant communities that emerge after a burn can help the recovery of an ecosystem's food web. Fire is still as important as it was back in caveman times, maybe even more so now. With proper education, controlled burns, and a healthy respect for the chemistry, fire will continue to be an invaluable resource to humanity. Hey, it's Miranda Cosgrove, your favorite host of Mission Unstoppable. I'm the only host. And if you want to watch awesome STEM videos and exclusive Mission Unstoppable clips, just make sure you subscribe and hit that notification bell.